Welcome to this EDEM webinar series, and today we are presenting how to simulate stone chipping using EDEM and MotionSolve, and we'll have the Q&A section at the end. Thanks very much for confirming, and now I will pass you to Prasad.
Thanks, Cesar. Good morning. This is Prasad from Altair, India, and today we will be discussing stone chipping. We will be discussing broadly about material, what kind of testing to be performed, and what is the calibration, and what is the parameters to be swept to achieve calibration for stone chipping, and finally the new technology from Pratt & Miller, who is Altair partner, about airless tires, how to model. We can see that capability as well. EDEM is a bulk material simulation software which is powered by discrete element method technology. So where EDEM gives a crucial insight about the bulk material particle to particle interaction, and as well particle to equipment interactions. So coming to today's discussion about the stone chipping, we will be primarily focusing on the gravel material instead of other material characteristics. Contact model classification in EDEM. So predominantly contact models are classified as two categories. One is incompressible material and the second one is compressible material. So if the bulk material is incompressible with cohesive in nature, then you have to choose Hertzmillion with JKR. If the bulk material is incompressible with free flowing in nature, then Hertzmillion no slip contact model is the right physics model. So all these four will be classified under the category of base model, and along with the base model, we have to define a rolling friction model. You can choose appropriate additional models, but in today's we will be going with Hertzmillion contact model, and then the wear models, because gravel will be incompressible with free flowing in nature. So Hertzmillion is the right contact model to choose for such applications. However, in stone chipping, one of the important criteria is wear modeling. So for the wear, arched wear, relative wear, or Oka wear is the contact models which is available in EDEM. We have to define the bulk material properties and interaction properties, along with particle shape, size, and its distribution, and then we have to perform the calibration, and then choose the appropriate physics or contact model. So this gives the complete scenario of the bulk material workflow to simulate any EDEM job. So to see about what is the Altair multiphysics capabilities with respect to EDEM, EDEM can be coupled with computational fluid dynamics to simulate fluid effect along with particulate material. And if you want to simulate structural strength, then we have a couple of methods. One is one-way method, that is one-way coupling, where you will be running the EDEM simulations and exporting the forces. Will be applying in FEA-solve called OptiStruct or in HyperMesh or in a SimSolid to assess the structural strength of the components. So in the other way, we have even recently released a two-way coupled approach where EDEM and OptiStruct will be coupled in a two-way, means the load will be transferring from EDEM to OptiStruct, and then OptiStruct will be performing the structural strength analysis. Then again, the new velocities and displacement will be transferred to the EDEM. So this way, we can able to couple EDEM and OptiStruct for two-way. And then today's topic predominantly is on EDEM plus multi-body dynamics, where Altair has MotionSolve as in-house multi-body dynamics tool. So why we need to go with EDEM plus multi-body dynamics as a co-simulation? So which EDEM plus MBD coupled simulation will help us to represent a complex dynamic our models, and which will give us a great insight about the process performance and optimizing the structural scenarios. And even we can able to validate the system dynamics, which is the realistic operating conditions. For example, so if the vehicle is moving on a gravel and due to different variation of the variable speeds, how the material will be lifted. At the same time, you can also see the similar operating conditions with different material characterization of the same vehicle, and try to understand and compare the performance of the vehicle under the different characteristics of the material, such as either the gravel or the clay or the soil, so which help us to predict the performance of the vehicle. So also, in general, as you know, the simulations will reduce the physical prototyping. So the two-way coupling will help us to represent more realistic scenarios. So today we will be more focused on EDEM plus MotionSolve, though we have different solvers can be coupled for MBD side with EDEM, which can be recorded on add-ons. But this webinar will be focused on EDEM plus MotionSolve as a software. So to understand how EDEM plus multi-body dynamics coupling works, just to give overview. So from the MotionSolve, we will be first transferring the geometries to the EDEM, and then from the EDEM we will be transferring the forces and the torque, whereas from MotionSolve the displacement and velocities of the CAD geometries will be new position will be transferred to the EDEM, and the data will be repeating for the time simulation time which we define. So when it comes to the applications, the key applications in automotive industry is stone chipping, brake dust application, and the snow accumulation is few of the key applications which we are focused as of now. Coming to the FlexTire, Pratt & Miller FlexTire, who is Altair partners. So where FlexTire is in, it's a coupled with MotionSolve and EDEM to run a tire for the realistic flexibility of the tire modeling. So which help us to model the soil to tire interactions more realistically. So where you can see here with how the tire the tire will get deformed, and the flexibility of the tire modeling. So which can be only possible with PM FlexTire. So also we can provide a time varying pressure instead of constant pressure. We can also allow the tire to take as input as a time varying pressure details, and soil to thread interaction we can model. And also the major physics how the tire model works is the tire components as carcass, belt, inner liner, and bead area will be treated separately, and which helps to more represent a realistic behavior. So if the tires get rigid, we will be but the PM FlexTire help us to model the real physical behavior. So to understand more about FlexTire coupling, how the data will be exchanged. So PM FlexTire will be come into action when only the tire model will be interacting with the soil, whereas if the tire model is in contact with the rigid road surfaces, then it takes the standard auto tire model from MBD solver. So how the data will be exchanging from FlexTire to EDEM when the soil comes into action is like the nodal displacements are calculated, with respect to the reference frames, and which can be shared back to the EDEM to calculate the contact forces. So at the same time, from initial forces or moments with respect to the global coordinates will be explicitly added to the total forces before calculating the nodal displacements based on the geometric transformation matrix. And now we will enter into the actual application, that's stone chipping. Yes, stone chipping briefly gives a definition of, when a stone impacts with a high velocity, the coating surface will get damaged. So major causes of the stone chipping is the paint damage and the scratches or dent, paint peeling or flaking. So there are various methods industry follows, depends on what kind of objective of their supplier, or if it's a OEM. For example, if the primary object is on only one specific product, so then the stone chipping will be performed in a different way. Or if it's a full vehicle system is of primarily important, then the stone chipping method will vary. So totally we have 4 methods available to perform the stone chipping. One is gravelometer based on SAE J400 standard, and the second one is injecting the gravel directly onto the vehicle underbody side from the tire. And the third one is moving a full vehicle over a large gravel bed or on a small custom gravel bed. So it depends on the customer requirement or the OEM standards. So the last one is about to have new paint coating techniques, which is out of simulation scope. But we will be covering in this webinar these 3 methods. That's stone chipping using SAE J400, and stone direct injection method, and then moving full vehicle over a large gravel bed and a small gravel bed. So before going to the actual application, the key parameter or step is material testing and calibration for stone chipping. So what kind of materials to be used and what kind of calibration to be performed, we will see before going into the actual application. So first, the classification of solid material, particulate material is we are choosing as a gravel, as I mentioned earlier. So gravels will be in the particle size typically ranges between 2 mm to 100 mm. So which was as a contact model as mentioned. It comes the classification of core solid, or you can say which can be simple to model as it's a free flowing material. So incompressible material with free flowing in nature, the tendency of the gravel material. So which can fit with Hertzmillian contact model. Now, so in general, the why we need to do calibration, and what are different key aspects we should consider into calibration is. For example, if you are looking at only the angles, for example, if you see the heap angle, which is obtained only alpha, which can be obtained through high friction and low cohesion case. At the same time, same alpha can be obtained with low friction and high cohesion as well. As if you go with only the magnitude of the heap angle, which may end up with wrong prediction. So that's where we always recommend to consider the flow behavior or the flow regime, and as well as the stress state of the bulk material. Meaning, for example, if the material is, as gravel we discussed, which is free flowing in nature with incompressible. So if it is a free flowing, the friction will be high possibility and the cohesion will be low. So this is the classification we can fit it. Whereas if you try to predict with high cohesion, so which goes with a wrong material calibration, and the simulation will become very difficult to get validated. So at the same time, not only the flow regime, we should understand what is the stress state of the material experiencing. So which gives what kind of calibration to be chosen. Typically, we recommend for stone chipping application for understanding particle-to-particle interactions and the particle-to metal or geometry interactions, or angle of repose and as well as inclined plane test. As static angle of repose will help us to give us the particle-to-particle interaction, which can be performed with simple pipe test, where you will be use a flat ground surface, and you can place a hollow cylinder over the flat surface, fill the material and lift the cylinder with a known velocity, which help us to predict the heap angle from the material flow behavior. And then to understand particle to equipment interaction, so we can perform inclined plane test, where you can put the gravel material over the flat plate and try to rotate the plate with a known angle. When the material starts flowing, we need to measure the angle at which the initial material starts flowing will be called as initial angle of slip, and the maximum material or the complete material flows out of the plane at what degree of rotation will be considered as final angle of slip. So these are the two angles to be measured, and the same angles to be calibrated by for adjusting the frictional parameters between particle to geometry, which help us to give the interaction parameter between particle to geometry. So for the stone chipping application, to perform to understand the particle to particle characterization, angle of repose test will be the recommended, and to understand particle to non-tire, for example, metal interactions, so inclined plane test is the recommended one. So what parameters in general we need to be calibrated? So most of you guys know we need to look for particle shape, size, and distribution. What is the bulk density of the gravel, shear modulus to be chosen. For the interaction parameters, we should calibrate coefficient of restitution, coefficient of static friction, and coefficient of rolling friction. So these are the parameters we should be targeting to achieve a calibrated material model. So when it comes to the particle shape, size, and distribution, so EDEM allows you to model any gravel using single sphere or with multi-sphere. You can go with polyhedral with different shapes like a cuboid, a prism, and a tetrahedron shape. Even polyhedral, for example, you can use pyrocylinder. Even combination of all these four shapes also possible. And when it comes to the distribution, EDEM allows to model fixed sizes, and normal, log normal, and even user custom defined distribution can be given as an input. So how to perform the bulk density calibration? So to summarize, how in the EDEM we will be given as a solid density, not the bulk density. How the solid density will be calculated is packing factor times the bulk density. In general, a random approach to fill a cube, which can the packing factor ranges between 60 to 59 to 60% of as a packing factor for randomly filled particles. Sorry, randomly filled with spherical particles. How the packing factor still will be calculated is, you can use the volume of the spheres divided by volume of the box. So this is the approach you can use start with the calibration, so that if you use the packing factor times multiplied by the bulk density, your number of iterations to achieve the bulk density calibration will be reduced. So how to measure the bulk density is, you should fill the material and use a sensor, density sensor, to the level lower than the free surface, and then which gives you constant bulk density. How to choose the shear modulus? So from this graph, which is plotted against shear modulus versus computational time. So if the shear modulus is 1e⁵, the computational time is very low, and if the shear modulus is 1e⁶, comparatively the shear modulus increases, whereas if the shear modulus is 1e⁷, meaning if we start increasing the shear modulus order by 10, means multiply 10 order, which computational time is drastically changes until gradually increases until 1e⁷, from 1e⁷ to 1e⁸, that is even 1 order increases from 1e⁷ Pascal to 1e⁸. It's nearly 3 times the computational time is increased, whereas from 1e⁸ to 1e⁹, the computational time is drastically increased. So we would recommend, you can go with the shear modulus 1e⁷ to 1e⁸. However, the calibration is to be performed, else you cannot able to get a realistic behavior of the bulk material. So why can't we go with the lower shear modulus? So for that, if you observe this picture, where we performed a angle of repose through a poured angle of repose, where we filled some material with a bucket and poured over the ground. If you see carefully, the physical behavior of the pile is completely different from the other 3 cases, which means lower the shear modulus, the real behavior was not more accurate. So hence the recommended particle or the shear modulus for the particulate material is 1e⁷ to 1e⁹. However, we will be recommending or suggesting to reduce the computational time for the shear modulus using 1e⁷ to 1e⁸ Pascals. So if the hardware, if you have a very good hardware, and if you have capable to run longer time and lower time steps, so then you can go with even higher shear modulus as well. So these are some of the examples of how to perform physical test in case of angle of repose. You can fill the material and lift the cylinder with a known velocity, and the same can be performed in EDEM as well. So that you can able to measure the angle from using the Python scripts which is inbuilt from the calibration kit, or we can measure from the protractor as well. So the physical test, how it performs, you have to do the same method to do the angle measurement for the heap angle. So how to perform a calibration test? Because the question always comes, generally we will try to scale the particles, or we will be for the gravel the particle size is large. How can we construct an equipment to perform a static angle of repose? Here is the information. So the first is we should calculate the mean particle diameter. So all the rest all depends on the mean particle diameter, where you can see the cylinder diameter is constructed based on 20 to 30 times of mean particle diameter, and the height of the cylinder to be considered as 2 to 3 times of cylinder diameter. So this is the some of the calculation which helps to construct or to perform angle of repose test, which gives an good correlation with respect to the physical test and EDEM, because this help us to avoid some of wall stress effects as well. If you go with these are the standard dimensions. So about inclined plane test, you have to consider the material, the equipment material as a plate, which is to be chosen for the study of wear or the key component. And you should pour the gravel or respective material and lift the plate, rotate the plate about an axis, and try to monitor at what angle the start material flowing will be initial angle of slip, and the maximum amount of material or the complete material flows down at what angle we should measure and name it as a final angle of slip. And the same will be measuring in the EDEM, that is the initial angle of slip and final angle of slip by adjusting particle to geometric frictions. So these are the calibration tests will be performed. And in summary, what we are achieving from the calibration test is particle to particle coefficient of restitution, static friction, rolling friction, at the same time particle to equipment restitution, static friction, rolling friction. For the particle to particle, shear modulus, solid density, Poisson's ratio are the parameters which we will be obtaining from the calibration. So now we'll see some of the stone chipping simulation setup. What are the key parameters which will be varied and study its effects on stone chipping. So we can able to vary the particles shape, such as multispheres or polyhedral elements. Even you can position, instead of vehicle moving over the straight surface or in the straight road, you can also study the vehicle when it is moving over a gravel bed on a left turn, right turn at different angular positions, so that which helps to understand what are the impacts and different components under the influence of different operating conditions. Also various suspension position, and also by varying frictional parameters and the coefficient of restitution, we can study the effect of stone chipping. And the output which is to be focused from the stone chipping is the trajectory of the particle due to vehicle movement, or after the impact of the particle, or after the lifting of the gravels from the tire and hitting the underbody parts of the vehicle. And also the force experienced by the body parts, wear and crack location, so frequency of particle hitting the body parts, and proportion of various size, shape of the particles hitting the body parts. So these are the key outcomes we can focus from the stone chipping simulation. What was the primary and secondary outputs from full fuel vehicles and in electrical vehicles? So you can see some of from the stone chipping, primary and secondary path identification. So some of the rust formation in critical areas. So location of stones hitting in the critical primary and secondary areas. The wear and damage of primary and secondary parts. The primary parts such as underbody, and the secondary parts such as the fuel tank, canister, metal pipes, fuel lines, and brake lines. Whereas in the electrical vehicle, so the key aspect is the rust and wear analysis on critical zones, and damage and damage to the primary parts such as the underbody, and secondary parts such as battery protection zones, and metal pipes and brake lines. So also we can try to identify the stones hitting the critical regions of the locations of the primary and secondary parts. So now coming to the gravelometer, that's stone chipping based on the methodology one, which is based on SAE J400, where the test equipment is shown here. So here this is a pipe, and the funnel will be placed here. The gravel will be loaded inside the funnel, and it will be flowing one after another slowly, and the compressed high air with a very high pressure will be injecting. Due to the high velocity or high pressure of the compressed air, the gravel will be hitting, and then it will be traveling along its path, and there is an object or the part which is the key part, which to be measured the force or the damage or the wear of the equipment will be placed at a distance given from the test standard. So this is the test specimen construction. So the same will be used. We can still use EDEM alone to simplify the simulation approach, even though the compressed air we can also include to avoid the complexity of simulation, or to reduce the simulation time. We can run EDEM alone simulation to understand the injection of the gravel, and due to the injection or the gravel impact over the object, what is the force the object is experiencing, and the amount of wear which can be subjected, can be predicted. As I mentioned, if we have calibrate and use appropriate Oka wear or archer wear, which help us to give us amount of material removed. As if you don't know and not able to perform a calibration about the wear, so then still we can able to use relative wear model to predict the wear region. So the second method is injecting the gravel directly onto the underbody through from the factory created along the tire path. You can see this is the factory and this is the tire, and the the gravel is injected with a known trajectories path. So we have to perform a test to understand the trajectory of the gravel versus the velocity with which the material flows. So this is one of the study where the particle injection, you can see the material is gravel is injected with a known velocity and the trajectory. So where the material will be hitting the underbody, and then we can able to study the impact of the gravel due to gravel impact. What is the force experiencing, and as well the wear also we can able to predict. So for example, if you see the injection, because of the injection of the gravel, if the particle flows towards inside the vehicle, and we are measuring, calling as a theta2, and if it flows outside the vehicle, which will be called named as a theta1. So larger the theta2 indicates a chipping area more. So ideally you should target the theta2 should be lower, because theta2 is the if the larger the theta2 as mentioned, the underbody parts will be subjected for more damage or wear. So here you can see that also we can try to understand or predict the trajectory of different particle sizes. In this case, 3 centimeters, 1.5 centimeter, and 1 centimeter particle size. How that after the injecting the gravel, the trajectory will be understand after impacting the underbody and subsequent parts. So this is the wear based on the relative wear contact model. So the potential possible wear regions we can able to see due to the gravel injection. So the third case is about the full vehicle moving over a gravel bed. So where you can see the gravel bed is constructed for the given dimension, which is 10-meter long, 4-meter width, and then height of 0.13 meter. So here different sizes we created, and the vehicle is moving at a speed of 75 kmph. And this model is modeled using EDEM plus MotionSolve and as well FlexTire. So which was three physics was involved: the particulate material and multi-body dynamics along with FlexTire capability. So this video explains a brief setup of EDEM of gravel bed, about how to create a 10-meter long bed and 4-meter wide and 13-meter, the 1.13 meter height of material. How to create a setup, EDEM setup. A small demo video is you can able to see. So here we are creating the bulk material with the known properties. After calibrating, we'll be giving the material, and we can here you can use still 3-sphere model. We can able to construct and update the properties with known size distribution. So which will be we can see name it as a small size particles, and another multi-sphere particle is added. So which is with an irregular shape, we can able to model it. So which is named as a medium-sized particle. So these are the two particle sizes chosen to demonstrate stone chipping application. So now we are defining equipment material properties. So here you have to choose the calibrated properties based on the calibration exercise what we are suggested, like static angle of repose and inclined plane test. So here we are creating the road profile in EDEM. So which is the start point of the road where the vehicle will be first placed, and then drives from the MotionSolve side. So there are complete road is splitted into 3 classifications: road starting, middle, and end. Why we constructed this way is so to easy identification of which region we need to create material. So initially we will be allowing the vehicle to be stabilized for certain length of travel over the rigid road, and in the middle layer we'll be creating the gravel bed, and in the last layer again a rigid road to after the gravel bed that vehicle to enter onto the rigid surface. So this is modeled to easy identification of the region where material to be created, and as well to reduce the material flow or the gravel flow, where we are creating a sidewalls and placing to reduce number of particles falling out of the gravel bed. So there is a vertical members which will be created either side of the middle region, that's the middle road where the gravel bed is created, which helps these vertical plates to avoid the material to flow out of the gravel bed. So these are the key steps, and we will be creating the factory. So here we can see the factory size and the position, where to be placed, what is the quantity of the material to be created. So all the setup was uh, defined. But in this video, we are not demonstrating the running the simulation, like how long it goes. So we showing the demonstration of simulation setup for creating the EDEM gravel bed. So, however, you can find these simulation setup files in Altair community very soon to experiencing the stone chipping application from user side. So for the factory to speed up the process, we are giving an initial velocity to create the particulate material. And as I mentioned, we'll be choosing a default contact model, that is Hertzmillin with standard rolling friction. So also to reduce the computational time, as our focus is on the middle region, because the gravel bed created it at the middle, and we are slightly extending the dimensions to see the forward the gravel movement as well. So once the setup is done, you can save the simulation file, and then you can go to the simulator and define the simulation uh, time based on the rally time stuff, fixed percentage of 20%, and you can allow the simulation time for 1 second to material to be created, and then get allowed to be set it. If you have a GPU solver, use appropriate solver engine and then run the simulation. So this is about EDEM setup. When it comes to MotionSolve, so we will be loading a pre-setup of full vehicle. We are not demonstrating the construction of the full vehicle because of the time limit. So, however, if you have a predefined low vehicle setup, and then we will be positioning or changing the key aspect, the time model. We will be calling the tire property FXT file, which consists of tire properties, and we'll be calling the road property file. So these are the key files where FXT file consists of the mass of the rim and the wheel of the what is the size of the wheel and the tire width and the mass of the mass details, and even the CAD file of the tire model. So all details will be placed in the .fxt, and the road profile data will be given in the RDF file. So once you load, and then you can check for both the tires, will be verifying right and left hand side tires, so which can be already assigned same properties of left side tire to right side. Then you can go to the flex tire, and then once you click on the generate, so there will be the GUI will open, where you'll be locating the DLL file, which in the EDEM bin, the step.obj, which is step.obj will help the FlexTire to model as FEMS, and also this will try to segregate the belt carcass in belt liner and bead off and inside of files, which will generate all necessary files. So once you click OK with appropriate settings, which helps to generate all necessary tire modeling files such as BDF, inside of, belt off, and So these are the PDF, OBJ, BDOF, built off, inside of all these files will be generated, and which will be stored with a property file, all the details. So this is about MotionSolve setup. Now, how to transfer the parts to EDEM? So for that, you have to select the necessary parts such as graphics. So underbody I want to transfer, and then vehicle body I want to transfer, and auto tires means the flex tire will also to be transferred to the EDEM. So once you go to the assembly, and there is a EDEM option where you have to select the EDEM and where you need to load the parts to be transferred from MotionSolve to the EDEM. So once you choose all the necessary files which to be transferred from MotionSolve to EDEM, activate the coupling server in the EDEM, and then click transfer and create a system. So what happens is the geometries, all the selected geometries will be transferred to the EDEM. So and then there will be DEM system to be created in MotionSolve side. And you can see here the tire and rim got segregated separately, where each rim you can assign appropriately to the respective tire, and here you can define a constant pressure for each tire. You can activate the flex tire, and you can call this dot flex tire. So what this flex tire will consist of is, when you transfer the flex tire geometry or the tire geometries, it will create all the necessary files of OBJ, BDF, inside of built of these files will be moved into a separate folder, and the file it will be created one text file with a file path. So that file will be called as a flex tire. So you will be loading that flex tire in EDEM by choosing the appropriate location and calling that flex tire file and giving as a constant pressure. So you can define for all the 4 tires, call the flex tire, and then define the constant pressure. So for the variable pressure, you can able to define in the FXT file. So as I mentioned, the each rim to be assigned a parent and child relationship with respect to the tire, so that based on the tire movement, the rim will be moved. Otherwise, the rim will be placed in the same location. The tire will be moving through because of movement, the motion from the MotionSolve. So once you define the setup, save the EDEM file, and you see there is a DEM0 is created when the system from flex tire underbody, the parts what are transferred from MotionSolve to EDEM. So this is the DEM0, which consists of all the data to be exchanged between EDEM and MotionSolve. So once this is transferred, then you can go to MotionSolve to submit the run using offline mode. You can define the run directory and run based on default analysis or so once you run the simulation, the coupling will exchange, and then will be similar co-simulation will be established, and vehicle will be the driver component should be from the MotionSolve, whereas in the EDEM only the gravel will be there. Once the flex tire will come into action because of flex tire, when it tire will be interacted with particulate material, then only the PM FlexTire will be active. When the tire is interacted with the ground surface or the road surface, flat surface. So in such case, the multi-body dynamics. In this case, it's MotionSolve tire will be coming into action. So just to give the requirements from the software side, PM FlexTire is available from the version EDEM 2021.1 or later. From the FlexTire, it's not a separate software, just a DLL file and a exe file to generate the mesh, and as well as the coupling DLL should be placed in appropriate location, and also from the tire data. So FXE file will be to be created with appropriate tire property data, and the CAD geometry to be placed. Tire CAD model should be placed, and handling tire property should be the necessary one. So these are the file formats and from the respective softwares. So when it comes to the FlexTire calibration, so you have to perform loaded radius versus load at different air pressures. So to calibrate soil to tire interaction in EDEM, you can see this is how you can perform calibration, where the tire will be compacted over a particulate material, and try to see the load radius, vertical load versus the load radius, tire load radius. So this plot will be try to calibrate, and also you can see the contact area shape and pressure distribution at different loads and air pressures also you can study. So this is the calibration method or the test recommended for the FlexTire. So if you want to use the FlexTire, you have to get a loaded radius versus tire load, tire vertical load data, and you have to perform the calibration. Very soon we will be releasing the calibration, how to perform the calibration data, all those details in Altair community forum. So these are some of the results from the gravel large bed case, and the last case is with custom gravel bed, moving vehicle over a custom or small gravel bed. So this is based on one of different ways to study. It depends on when there is no standard method, so you can try to follow a custom method from your side by developing a small material over the flat surface and moving the vehicle over the gravel. So because of the time constraint, I'm skipping some of the results, where you can see the gravel vehicle moving over a gravel, lifting the material, and how it impacts the underbody and other parts. So we can try to find out the material or the number of particles. For example, what is the kind of small particles, medium or large particles, or what is the total number of particles at each time interval we can understand. And the wear we can able to try to predict. So this is the wear model for comparison, though it is not relevant for this case, but this is a generic information about wear model, where a relative wear model will give you the wear information, whereas the Archer and Voca wear will give you the amount of material removal. Even EDEM has a capability to predict the geometric deformation for the material removed over the surface by enabling geometric deformation in EDEM wear mode. So the key points in wear is you have to remember that the mesh size or the element size should be larger than the particle size. So otherwise your wear is not uniformly distributed. So these are some of we are skipping for the time constraint, and the last capability is about the airless tire. So how different this airless tire capability with respect to FlexTire is if you make the tire pressure 0, so which means it becomes airless tire. So I will stop it here, and if you have though there is a few we can have a couple of minutes to have a Q&A. Caesar.
Hi, Prasad. Thanks very much for the presentation. Also, this topic is quite broad. If any of you have any questions, please just let us know now in the Q&A. Also, we can follow up in support as well. So we have a question here: how the rigidity of the tire is defined in FlexTire? Can you change that value?
Sorry, Caesar, can you repeat?
So can you change the property of the tire during the simulation?
No, it is in the FXT file you have to define initially the properties. So once you define, it is fixed for one simulation. So the properties should be obtained from the FlexTire calibration. Else, the results are not validated against the physical test.
Also, there is a question here about contact models. Which one is recommended to use when we have high contact moisture, around 40%?
When you say high moisture content here, if it is a slurry, then we currently don't have any model. However, you can go with for a representative simulation with JKR with very high cohesion model, or if the moisture is saturated condition, then there is a new contact model, that is the lubrication contact model, which is based on hydrodynamic effects are included. So you can go through the lubrication contact model reference information. If it fits, you can choose that contact model as well. But however, those two models, either a high cohesion or the lubrication model, will give you a direction, but not, you cannot able to, those are not the right model, because 40% of moisture will be generally, it's a slurry condition.
Can we simulate the wear of the tire? So I'm talking about the lifespan of the tire.
So lifespan of the tire, you can able to see the durability, or in general the wear and tear will help you to understand how long. Maybe we can we may not able to get it right information from these studies for durability, because each OEM will be followed different method. So in general, like for example, if it's a metallic conditions, if you see fatigue calculation will help us to figure it out for the life. But for the tire, if you say life, what is the parameter you verify? So based on that, we can recommend the methodology. For example, if you consider the tire tread wear, so then we have directly the wear measurements. Apart from that, we don't have any other measurement to assess the life of the tire.
Thank you. And if you have any other question, please let us know in Altair support. Thank you, and bye for now.
Thank you all. Have a good day.